All right, sulfur nucleophiles. And hopefully you remember that sulfur is in the same group as oxygen, right? It goes oxygen, sulfur, right? They're right on top of each other. So since they're in the same group or the same family, they behave similarly. And so just like a ketone or an aldehyde will react with an alcohol in the presence of a catalytic amount of acid to give you an acetal, if we have two equivalents of a thiol, so this is what we call a thiol, it's the sulfur analog of an alcohol. So if we have two equivalents of a thiol plus our ketone or aldehyde, catalytic amount of acid, we end up with a thioacetal plus water. So the mechanism is going to be the exact same as the formation of an acetal when you make a thioacetal. And just like we saw with our alcohols, we could use two equivalents of an alcohol, or we could use a diol like ethylene glycol. This diol would be called, this would be called 1,2-ethane dithiol. Okay, the name isn't all that important, but in that case, you'd end up with a cyclic thioacetal. Now you might be saying, okay, well, you taught me how to make an acetal, which has oxygens. Now we're learning how to make a thioacetal. Why would I even want to make a thioacetal? It's a good question. And the reason why you would want to make a thioacetal is because it gives you another way to reduce down to an alkane. So check this out. You can do this reaction. This is called desulfurization. And desulfurization is done with something called Raney nickel. Okay, so Raney nickel is actually like a nickel aluminum alloy that has hydrogen absorbed on the surface. And so the hydrogens replace the sulfurs. So literally the sulfurs go away and they just get replaced with hydrogens. And so this gives us another way of reducing a ketone or an aldehyde down to an alkane. So we can make our thioacetal from our ketone using a catalytic amount of acid and our dithiol. And then once you're done that, once you've made the dithiol, you just treat it with Raney nickel and you reduce it down to an alkane. And if you have a good memory, which I know you all do, you're probably thinking, well, you also taught me how to reduce a carbonyl down to an alkane using a Clemmensen reduction. True, we learned the Clemmensen reduction and the Wolff-Kishner, right, where we made the hydrazone and then we just treated it with some potassium hydroxide and heated it up. So now you have three different ways to effectively take your ketone and reduce it down to an alkane. You can use Raney nickel, you can use a Clemmensen reduction, or you can use a Wolff-Kishner, and students have to know all three. Okay, predict the major product for each of the following. So here we have a carbonyl. In the first one, we're treating it with a catalytic amount of acid in our 1,2-ethane dithiol. That is going to give us, so I'll circle that in blue, that's going to give us our thioacetal. So I'll just scribble it down here quickly. It's not asking us to draw this, but we'll just put it in here. So there's your thioacetal. That's going to be your intermediate. And then in the second step, you're treating it with Raney nickel. Well, that's going to reduce it all the way down to an alkane. And so you're going to end up with this compound. There we go. The next one, same reagents, okay? In the first step, we're going to treat it with a catalytic amount of acid in our 1,2-ethane dithiol. So we're going to take that aldehyde now, and we're going to replace it with our thioacetal. There's nothing wrong with the structure that I've drawn here, but if you want to include that proton, you can, okay? But now, when I reduce that with my Raney nickel, so what am I going to end up with? I mean, you could draw it like this, hydrogen, 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 like this, but you can see that this is the same thing as 2-methylbutane.